And this one, let's take a look at using rational roots theorem and synthetic division to factors. So we have the following as an example. Imagine you have z cubed plus 2z squared minus z and then minus 2. So let's factor this synthetic division in the rational roots theorem. The rational roots theorem states that the possible rational roots are basically the ratios of the factors of the last term and the leading coefficients. So in front of the z cubed, you can imagine it's always like, for example, 1 positive. So let's see, the factors of last term. That means the negative 2 essentially. I can list those out. There are not too many of them. Plus 1, negative 1, plus 2, and then negative 2. Those are the factors of the last term because 1 can be divided into negative 2. Negative 1 can be divided into it. So can positive 2. So can negative 2. The factors of positive 1. That's this positive 1 from here. Let me grab a different color, right? The factors of that 1. And then over here, let me also do this. The factors, remember, these were the factors of the last term. That means the negative 2. Alright, so with that in place, the factors of the blue one, they are basically positive 1 and negative 1. Which means by the rational roots theorem that the possible rational roots would be a ratio of the factors of the last term and the factors of the first term. So let's go through that. Imagine if you take the 1 and the 1 from here. Well, 1 divided by 1 is 1. Then you take 1 and a negative 1. 1 divided by negative 1 is negative 1. You're taking the factors of the last term and you're dividing each of those by each of the factors of the leading coefficient. That's what you're doing essentially. Move on here. Let me erase these little arrows. Make my eraser smaller. Erasing. Then I'm going to take negative 1, but look carefully at negative 1. Negative 1 divided by positive 1 is already in the list as negative 1. Negative 1 divided by negative 1 is already in the list as positive 1. So I don't have to list those again. Then I'm going to take positive 2, divide by this positive 1. Positive 2 divided by 1 is positive 2. And positive 2 divided by negative 1 is negative 2. That position is good. Little arrows above the factors. And then negative 2 divided by positive 1. Again, that's already in the list as negative 2. Negative 1, that's already in the list as positive 2. So I can stop. I've done all the possibilities here. Now based on this, I'm going to now use synthetic division. So you try to make one of the roots work as follows. Set up synthetic division. Imagine I use the positive 1 first as an example. I'm going to put 1 in this. Put the coefficients from the upper row of the synthetic division. So 1, 2, negative 1, and negative 2. So 1 times 1 is 1. Negative 1 times 2 now, as you can see, is 1. The problem is that now negative 2 plus 1, that gives you negative 1. The remainder is not 0. So when the remainder is not 0, that tells you that 1, right here in this position, this 1, right, that's not a root. Because the remainder right here in the last position in the circle is not 0. So then you try with negative 1. Negative 1, then you have here the following 1, 2, 2. So you bring that down, so it gives 1. 1 times negative 1 is negative 1. Bring that down. 2 plus negative 1 is 1. 1. Add that. So negative 1 and negative 1 added straight down. Negative 2 times negative 1 is positive 2. Now when you add these, look what happens. You get a 0 in this position. You see? The remainder is 0. Remainder is 0. When that happens, that tells you that negative 1 is a root. And then from there, what you can do is the following. Remember that our root, from the perspective of a factor, is always the opposite of what's in a factor. Again, remember, this right here, since this is our root, and I know it's our root because the remainder is 0, I can use the root to write a factor of the polynomial. Upper right hand side, I'm going to say factor of polynomial. I'm going to call that poly. So you're beginning with the root of 1. It's this right here. It's coming from here. I'm taking that negative 1 where the arrow is pointing. It's a value of z. It's a root. And then based on that, look, you add 1 to both sides, so you end up with z plus 1 equals 0, which means this z plus 1 now is a factor of the original polynomial. Now, you have to finish up. You take these, and remember that they correspond to decreasing powers of z. So this is z squared, that is plus z, and this is minus 2. Now z squared plus z minus 2 can be factored further, so specifically it means the following, that I need two numbers that, take a look. The two numbers have to multiply to negative 2, have to give a value of positive 1. So when I do that, give 2, 1 positive is negative 2, plus 1 is not positive 1. So that line is no good. I need to change the signs. That doesn't work, in other words, okay? So I'm going to change the signs. Let me erase these right here. Erase that. 2 times -1 is -2, and then +2 plus -1 is +1. So it means over here when I factor, I'm going to have z minus 2 and then z minus 1. So the other factors of the polynomial come from factoring the quotient. The factored form overall is a factor from the root up here. This is the factor from the root where I've just drawn the arrow, that's z plus 1. And then the factors from doing z squared plus 1z minus 2. So those factors are z minus 2 and then... So the final factored form according to this process of the polynomial is z plus 1 times z minus 2 times z minus 1 again. Now do keep in mind that obviously if you look carefully at the polynomial, perhaps you could do this with factoring by grouping, but in many other cases you cannot use that method. But I wanted to deliberately choose an example where you could do it factoring by grouping, because then you can see that how the result is formatted, and at least then you have a way of checking that if you do this with factoring by grouping, for example, you'll get the same thing. This procedure works. This is a simplified example compared to what it could be, because obviously you could have a higher exponent on the leading term like z to the 5th or 4th, and then on top of it you could have bigger coefficients. So this gets at the essence of the method.